So today we are going to discuss about the state space representation of a linear time invariant systems. So this is of our last unit. Can you see the PPT, all of you? Is it visible to you? Is it visible? Okay. Okay. So we'll discuss about the state space representation of a linear time invariant systems. So in this, we are going to deal about the state variables of a dynamical system. Okay, so what is a state variable equation? Why we need to go for the state space approach? Okay, so by using a transfer function or differential equations or from the mathematical or physical parameters, we represent our system in the form of a state variable equation format. And one more topic is we'll see the derivation of a transfer function from the state space equation. Okay, vice versa. State space equation to the transfer function and the transfer function to the state space equations. And we also see the controllable canonical forms, and we'll see the time response of a system by deriving the state transition matrix. And at the last, we'll see the controllability and observability of the systems. So these are the important points regarding the state space and analysis of a system. Okay, so why we need to take the state space analysis? Okay, so what are the disadvantages of a classical control theory, and what is the advantages of a modern control theory? Okay, so the first 4 units which we have discussed are nothing but the classical control theory methods. Okay, and the last unit we call it as a modern control theory. So in the classical control theory, such as the root locus or Bode plot or Authorwich criteria, what we are seeing here, so it is depends on a transfer function approach. So always the transfer function approach is used, or the open loop transfer functions are used to find out the response of a system. So this transfer function is based on the relationship between the input and the output. Okay, so this method do not use any knowledge of the interior structure of the plant. That means it is not giving you the mechanical or electrical. It is not useful here. Okay, just we are writing the transfer function approach in terms of S domain. Then we are applying the single input, which are called as a step input or ramp input. These are the basic inputs. Okay, so that is called as a single input and single output system, which we are using for the analysis of a time response or frequency response. And here these methods will not give you the sufficient information in the time domain and also in the frequency domain if the order of the system increases. So it will not give you the relationship or analysis for the multi-input and multi-output systems. So it is very inconvenient method for the multi-input and multi-output systems. Okay, so because of this, and also the classical control theory is useful for only a linear time invariant systems. Linear time invariant systems. So for time variant systems, these methods cannot be useful. And that's why we are going for the state space analysis. So this state space analysis having the some advantages, such as it will consider the previous values which are stored in the system, or which call it as the initial conditions. So in a transfer function approach, we are neglecting the in the transfer function approach, we are neglecting the initial conditions. So here, this is the transfer function. So initial conditions, which are nothing but I naught of t, that is the current initial current across the inductor, or initial voltage across the capacitor, which we are not considering. But this will give you some effect on the system performance. So this is lacking in case of classical control theory, but it is possible with the modern control theory, which has a state space analysis. We can use these initial conditions into the system so that we can estimate the output over a all variable parameters. So this can be applicable to the nonlinear and also for the time varying systems. And this classical method can also be used for the multi-input and multi-output systems, multi-input and multi-output systems. And this will give you the optimal values whenever it is designed. So any type of input can be considered, not only the step input or standard step signals like step input or ramp input or parabolic inputs. Okay, so again, by using this classical method, you can represent the uh, algebraic equations in a matrix form, and this algebraic equations can be put in a matrix form, and it is very easy for the analysis of matrices using a digital computers. So these are the major advantages of a modern control theory over the classical control techniques. Now we'll see what is the concept of a state. So we are calling it as a state space analysis. So what is a state? Okay, so anyone, can you answer what is a state? What is the importance of a state? Just you answer it in the chat box. Anyone, can you answer what is a state? So here we see that if you see that your a football match is going on. Okay, if a football match is going on, then we'll count the goals. We have to count the goals. Both the teams are making a goals. So how we count? Normally we count the goals from the starting point, and we can add up the goals which are done by the teams, and finally we take the total number of goals done by each team. Okay, so we will announce that which team is made more number of goals. Am I right? So here the past input is required or not. Past means the starting point to the ending point. So that means 0 to time t naught. If you assume minus infinity to plus infinity, as the time is varying from 0 to infinity, we need to take the time from 0 to infinity. Okay, so that information, the past information, which is known as a state of a system, so which is lacking in case of classical control theory, as we are neglecting the initial conditions. Okay, so let us take the example of electrical system here. So here the output of a, what is the output of this uh, electrical circuit, which is called as a V output. Okay, so V output will be equal to the voltage across the capacitor. Voltage across the capacitor. So here this voltage across the capacitor will be equal to, normally we can call it as a V input. Okay, because the voltage, all the elements are connected in series, parallel, and therefore the input voltage will be available across the capacitor. But here some initial voltage also present in a capacitor, that voltage has to be taken into consideration. So your output will be varying with respect to the time t tends to or t greater than or equal to 0 as the time progresses. Okay, so your input only not giving the output voltage. So if there is no initial voltage here, if there is no initial voltage across the capacitor, then your output will be equal to input. And you can find out the transfer function as a V input divided by V output divided by V input. So directly you are getting a transfer function. But whenever there is a voltage across the capacitor, initial voltage across the capacitor, as the time t progresses, uh, your voltage will be changing, and this type of systems are called as a dynamic systems. So these are called as the dynamic systems because they will have the memory. Dynamic is nothing but they will have the memory is nothing but the initial voltage across the capacitor. Okay, let us assume that if this is only a resistor, this is only a resistor R output. So what is the V output for this circuit? V output will be equal to the voltage across the resistor. So this is equal to V input. Okay, for time t greater than or equal to 0, as the time progresses, there is no change in your input. So such type of systems are called as the zero memory systems or static systems. These are called as the static. If you replace this with your capacitor will be replaced by a resistor again here, and therefore your output voltage will be constant and which is equal to V input only. So this type of systems are called as a static system. Okay, so as the time progresses, there is no change in the voltage here. So the voltage will be constant, which is equal to the input voltage. So your output voltage will be depending on only the input. That's why this is called as a static system. And your whenever this a capacitor is there, it is stores some energy and is your output voltage will be depends on the input as well as the initial conditions of the system. So this type of systems are called as a dynamic systems. So well, let us take another example here, the mechanical system. So if there is a force which is applied on the mechanical system, so there is an equal and opposing force as per the Newton's law. Okay, so which is nothing but F is equal to m into A, and you can represent this as a F is equal to m into dv by dt. dv, this is the velocity of the system, dv of t divided by dt, and from that the velocity component, if you take up in integration for both the sides f, okay, with time minus infinity to 0, minus infinity to plus infinity, or this here also minus infinity to plus infinity, then you can also take this is a time t, alpha can be taken, infinity can be taken as a any time t also. Okay, so here if you do this, the velocity component v of t will be equal to, the velocity component v of t will be equal to 1 by m. This is a moment of inertia here, coefficient m into minus infinity to t, minus infinity to t into f, the function f or f of t. Okay, you can take this in time, f of t into dt. Then you can divide this time intervals into two cases. One is minus infinity to 0, okay, or we can call this as a t naught into f of t into dt, f of t into dt plus 1 by m into 1 by m into integration of t naught. This is the time t naught to t, and again f of t into dt, f of t into dt. So this value, the negative value, we can call it as a v naught of t, that is the initial velocity of the system, v naught of t, okay, plus this function, okay. So this function t naught to t t naught to t into f of t into dt. And therefore the velocity of this body will be depends on the two factors, which is not only on the applied force, and it is also on the initial velocity. So this is called as a memory. So this initial conditions will be called as a memory, okay. And so this will change the velocity of your system, and that's why the complete response of any system will be depends on the state. So what is the state of art normally? So the state of a system, and also for the state of the system for t less than 0 and t greater than 0. So this will be considered as a state. Okay, so the state can be regarded as a, or considered as a compact and concise representation of the past history. So this is a past history of the system that is representing the state of a system. So oh, now we'll define the state. Okay, so here let us consider a system which is having a n number of state variables. Okay, and u, these are the r number of inputs, and it will having the p number of outputs. So this is a system now. Okay, so this is a system. For this system there are r number of inputs. So this is a multi input multi output system. So r number of inputs and p number of outputs are there, and the system will be having a n number of state variables. So here what is the state? So the state of a dynamic system is the smallest set of variables, which are called as x1, x2, and also xn, called as the state variables. These are called as state variables or a state vector, such that the knowledge of these variables at time t is equal to t naught, together with the knowledge of the input for t greater than t naught. Okay, so here in previous case, this is the state variable form for a time t is equal to t naught together with the input function. Input is nothing but f of t. Okay, so together here the state knowledge of these state variables at time t is equal to t naught together with the knowledge of the input for t greater than t naught completely determines the behavior of the system for any time t tends to t naught. So, how many number of state variables are present in a dynamical system? So, the number of state variables in any system will be equal to the order of the system. So, the number of integrators involved, or we can directly call it as the order of a system. So, any system here which we can be represented by its mathematical equations. So the order of a system will decide the number of state variables. So if you take up the second order system, if you take up a second order system, so second order means normally this will be represented as omega n square divided by s square plus 2 zeta omega n into s. This is the standard form. Okay, omega n square. So the order of a system 2. So there are two number of state variables which can be called as a x1 and x2. So here the order of a system will be depends on the number of energy storage elements. Already we have seen. So the order will be depending on number of the energy storage elements present in the system. So energy storage elements. So if you have a RLC, okay, so this is RLC circuit. So L and C, these are the two energy storage elements. So if you find the transfer function, this is of the form of this second order system, and therefore there are two state variables present in a system. So what are the stores? What are those two state variables? Are normally taken as the current through the inductor IL of T, IL of T, the current through the inductor, and voltage across the capacitor. These are the two state variables you have to consider for a given system. So if you assume that there are three energy storage elements, okay, so L1 and this will be C2, okay, C2 and the C1. So you have to take that the current through inductor. So there are three state variables, Vc1 of t and also Vc2 of t. Vc2 of t. So there are three state variables present in a system, and those are assumed as the current through an inductor, voltage across the capacitor 1 and voltage across the capacitor 2. So like that you have to consider these state variables for a given system. Okay, so here the system is the multi-input and multi-output system, which involves n integrators. That means n number of state variables, and also there are r inputs. Inputs are represented as a u of t. Okay, so here these are the inputs u1 to ur of t, and the p number of outputs y1. So these are the outputs and these are the inputs. So now by using this, you can represent the state space representation as the state equation. There are two equations which are called as a dynamic equations. Okay, one equation is called as a state equation, and the another one is a output equation. So this is a representation of a state space. Okay, so the state space representation is consisting of two equations. One is state equation and another one is the output equation. So the state equation is nothing but x dash of t, which is equal to a into x of t plus b into u of t. So these are the state variables. X of t is nothing but the state vector. So this is known as a state vector, and this is known as an input vector. So u of t. And similarly here, y of t is called as an output vector, okay, and x of t is again the state vector, and u of t is the input vector. And from this, the matrix A, so we'll see a matrix here because there are n number of state variables, so you have to write that the equations will be in this form. Okay, so this is a into x term. Okay, so this is a plus b into u. Okay, so these are the inputs. So these are representing the inputs, and this is a matrix B, and this is a matrix of state variables X, and this is a matrix of A. So resultant will be again a matrix of state variables X dash. Okay, so this matrix A is called as a system matrix or state matrix, and B is called as an input matrix, C is called as an output matrix, and D is called as a feedback matrix. So we'll see what are the order of these matrices. Okay, so here for this for the state equations, so x of t. x of t is consisting of x1, x2, and so on. Xn, there are n number of state variables. So the matrix will be sized as a n by 1. And your u of t is called as an input vector. So there are r number of inputs. So you'll have a u1, u2, u3, and so on ur. So this is also a column matrix, and this is also a column matrix. Okay, so y1 of t, this is an output matrix. Okay, and x naught, these are the initial conditions. These are called as the initial conditions. And now the matrix A is having a n by n. Is a model which is representing the matrix as a n by n matrix, and B is called as n by r matrix, n by r, and C is a p by n because it is a p is the because p is nothing but the number of outputs. So here output, this is having a p by 1, so p by 1, and therefore this is x of t is having a n by 1. So your C should be having p by n, p by n. Here x is nothing but n by 1. Okay, here 1 by n. Okay, x of t is also having n by 1. This is having n by 1 normally. This is having n by 1. And therefore, the matrix A will have n by n. Okay, and like that, B is having n by r, n by r. Okay, this is n by 1, n by 1, n by n, n by r. This is n by r because inputs are r, and D will be having p by r because this is a p, and u of t is having r by 1, and here this is also having r by 1. So p r, so this will be having p by r. Now we'll see the basic representation of a state equation. Okay, so we have seen that x dash of t will be equal to a into x of t, a into x of t plus b into u of t. So we have to represent this, and y of t will be equal to c into x of t plus d into u of t. So x dash. So normally we'll take this one as a node x dash of t. Then if you integrate this, okay, 1 by s. If you integrate this, you will get an x of t. And then this is a summing point. So where the two signals are added up here. Okay. So your input u of t and your output is y of t. Then we need to get x dash of t. So x dash of t will be equal to a into x of t. So this is a into x of t. So this should be plus here. Okay. A into x of t plus b into u of t. So this signal u of t should be multiplied with a matrix B, and this should be added here. So we'll get x dash of t. Then if you integrate this, you'll get x of t. Then your output equation y of t will be equal to x of t into c. So this is a c into x of t is coming here, and d into u of t is coming here. So your output y of t will be equal to c into x of t plus d into u of t. So this is a block diagram representation of a state space model. Now, so the state space model versus the input and output model. So in the state space model, we'll consider all the internal behaviors of the system, which includes the initial conditions. So this methods can be easily incorporated complicated output variables also, and have a significant computation advantage for computer simulation, and can represent the multi-input and multi-output systems, and also the non-linear systems. But the input and output models are, uh, as per the concept wise, it is simple, but it is easily converted into frequency domain. But though they are difficult to solve in time domain, they are difficult to solve in time domain. So now we'll see some definitions of a state space analysis. So the system variable. So variable is that represents an input or initial condition in a system. Variable means it is a state variable. So x of t or vc of t, whatever we are assuming it. Okay. So state variable is one that represents the input or initial conditions in a system. So if you take up an RLC circuit, so I naught of t or IL of t, IL of t or the voltage across the capacitor Vc of t. So these are the two state variables which are representing the initial conditions in a system. So next one is a state variable. State variable is a smaller set of linearly independent system variables such that the values of the members of the set at time t naught along with the forcing function, which is called as the input, completely determines the value of all the system variables. Okay, then what is a state vector? So a vector whose elements are the state variables. That means when you want to represent in a vector formation, the elements on this vector should be all the state variables. In the state space is an n-dimensional space where axes are the state variables, where all the axes are the state variables which are known as the state space. And also the state equations, they are the first order differential equations with b variables where n variables to be solved are the state variables. Okay, so there are n variables are present in the system, so those variables can be solved. And also the output equation, it is algebraic equation that expresses the output variables of a system as a linear combination of the state variables and also the inputs. Okay, so the state equations will consisting of the initial variables x of t plus inputs, and your output is also a combination of state variables and the inputs. Now, so how we represent the state space equations. Okay, so select a particular subset of all possible system variables. So we call them as a state variables. And for nth order, write the n simultaneous first order differential equations. We have to completely write up only the first order differential equations. Okay, so in terms of state variables, we call it as a state equation. We'll see how to write all this. Okay, so first of all, what we are doing, we are choosing the system variables. They are called as a state variables. So if you are having a RLC circuit, so the state variables are chosen as the current through an inductor and voltage across the capacitor. Or if you want to find out for the mechanical systems, so velocity and force are considered as input and state variables. Okay, so now once the state variables are chosen, then we have to write up the first order differential equations for that. If there are two state variables are available, so you need to write up only the two simultaneous equations of the first order. So those equations are called as the state equations. So you'll get the state equation in terms of state variable and also in terms of the input variable. Now, if we know the initial condition of all the state variables at time t naught as well as the input for t greater than t naught, then we can solve these equations. Okay, so if you know the initial conditions and also the system input, if you know the input and the state variables at time t naught, Then you can easily solve the equations. So now we'll represent the state space representation of an nth order uh, systems of linear differential equations. So here consider a system here y n dash. So this is a y n dash plus a1 into y n minus 1 dot. Okay, so this is a dot y n dot and so on a n minus 1 dot plus a n into y. This is equal to u. Okay, so this is a nth order system equation, differential equation, where here y is the system output and u is the system input. So y is the output of the system, u is the input of the system. So this is given to you. The equation is given to you. So we need to write the state space equations for this differential equation. Okay, so the system is of nth order, then it has n number of integers. N number of integers are called as n number of state variables. So these state variables, we are assuming it as a n number, x1, x2, x3, and so on, xn. These are the state variables. And we are assuming that these state variables for the given differential equation as the first x1 is equal to y. X1 is equal to y. So that is a nth order equation of the output. Okay. So x2 is equal to y dash and x3 is equal to y double dash. Okay, and so on up to xn is equal to y n minus 1 dot by n minus 1 dot. So this is the assumption of a n state variables. So here you are not given with any circuit, only a differential equation is given to you. So by using this differential equation, we need to draw the state variables and state equations. Okay, so what we are assuming here is just we are taking a state equation of x1. Okay, because it is an nth order system, you will have a n number, so and so on, x1, x2, and so on, xn you will have. And here x1 will be assumed as this will be equal to y. Simply you take up this x1 as y and x2 is equal to y dash. We'll see how to write this. Okay, and so on, xn will be equal to y of n minus 1 dot. Okay, so these are the state variables assumption. Now once you assume that, so what we are assuming here, x1 is equal to y, okay, and x2 is equal to y dash, and so on, xn minus 1 or xn is equal to y power of n minus 1 dot. So this is the assumption what we have made. Then from this, x2 is equal to y dash, x2 is equal to y dash. That means here this will be equal to x dash. Okay, from this you can assume this one. Okay, so when we need to write up the state equations, normally the state equations will be represented like this. X dot will be equal to a into x plus b into u. Am I right? So x dot. So we need to take up the differentiation of these state variables so that you'll get the equation in terms of x and also in terms of the input u. And that's why I'm taking x1 dash. Okay, initially I assume that the state vectors are x1, x2, and so on, xn. Then what I am doing here, I'm taking a differentiation of this x1 dash, x2 dash, x3 dash, and so on, xn dash. Now, what is x1 dash? So from this assumption here, x1 dash will be equal to, so here x1 is equal to y. That means here x1 dash is equal to y dash, and that means y dash is equal to x2. Y dash is equal to x2. That's why here I'm taking x1 dash is equal to x2. X1 dash is equal to x2. So similarly now x2 is equal to what? What I'm assuming here, x2 is equal to y dash. X2 is equal to y dash. But now x2 dash is equal to y double dash. Okay, so y double dash here, what is y double dash? This x3. x3 is equal to y double dash. And therefore x2 dash is equal to x3. And that's why here I am assuming x2 dash is equal to x3 and x4 dash is equal to x x3 dash. This is x3 dash is equal to x4 and so on. Xn minus 1 is equal to xn. xn. Now xn dash will be equal to normally xn dash will be equal to yn dash yn dash. All right. So here xn is equal to yn minus 1 dash normally. So xn dash is equal to xn dash. So here like this. So xn is equal to yn minus 1 dot yn minus 1 dot, and therefore xn dot will be equal to yn dot. So as we know that yn dot will be equal to, our equation is yn dot plus, so here a1 into yn dot, this is yn dot. Okay, so plus a1 into n minus 1 dot plus a2 n minus 2 dot. Okay, and so on plus, what is the equation here? a n minus 1 into y dot plus an into y. This will be equal to u. This is equal to u, and therefore, so from this xn dot will be equal to yn dot. So yn dot, this yn dot will be equal to, so u, this is a plus u minus of all these terms, which are nothing but minus an into y, y is nothing but x1. Okay, and plus minus an minus 1 into x2 and so on up to a1 into xn. So this is your equation. So the state equation is nothing but x1 dash is equal to x2, x2 dash is equal to x3, and so on. Xn minus 1 is equal to xn, and xn dash will be equal to minus of an into x1 minus a2 x2 and so on minus a1 into xn plus u. And therefore you can write up this state equation as x dot is equal to ax plus bu, and therefore x1, the state variable here, x1 is equal to, state variable is here x1. Okay, so your matrix will be represented like this here. So I'm writing here the same matrix. Okay, so the x dash will be equal to, this is a matrix A, let us assume. Okay, so this is x1 dash, this is x2 dash, and so on xn dash. Okay, which will be equal to x1, x2, x3, and so on up to xn. Okay, so I'll take another color here. So this is my input, okay, which is x1, x2, x3, and so on up to xn. So this is state variable x dash. X dash will be equal to x1 dash, okay, and this is a x2 dash, and so on. This is xn dash, and therefore, what is the value of x1 dash now? X1 dash will be equal to only x2. So only x2 means 0. The first term will be 0, and the second term will be 1, then 0, and 0 always. Okay, and then next x2 dash will be equal to x3. So plus you can also write these values. So you can also write the b and the u. U is only one. So if the first one is 0, the second one is 0, because these terms will not included with the zeros. Okay. So x2 dash will be equal to x3 only. So x1 is 0, x2 is 0, x3 is 1. The remaining terms are zeros. And like that, x3 will be 0, 0, 0, 1, and so on. Okay. So your final value will be now minus an minus an minus an minus 1 and so on up to a1. Okay, and this last term will be 1 because all the remaining values are 0 because the input only present for the xn dash, and therefore we'll get an equation for xn dash will be equal to u. So that this value will be a. This is a matrix A and this is a matrix B. Let us see this. Okay. So here x1 will be equal to 0. Okay. 1, 0. So the matrix state matrix A can be represented as 0, 1, 0, and so on 0. So 0, 0, 1. So like that, this is a matrix A and this is a matrix B. Okay, so this is a matrix B which is having only all the terms will be 0, 0, 0, but the last term xn dash will be having a input. So that's why it is writing as a 1. So similarly, your output equation is y is equal to x1 only. So we are assuming that y is equal to x1. So y is equal to c into x. So c will be equal to 1, 0, 0, and so on. So this is the n by c matrix will be written as p by n. P by n. So there are p number of inputs and p number of outputs and n number of state variables. And therefore the matrix C. And what about the D? The matrix D will be 0. There is no input is connected here. So output is equal to only x1. So this matrix plus du is there. So D is equal to 0 because input is not connected. So your feedback matrix will be 0. So this is a representation of a state space, state equations for a given differential equation. So this is a procedure you have to follow for any differential equation of the form given to you. Okay. Then next, we have to write the state variable equations for a given mechanical system here. So for this system, when we need to write up the state variable analysis, so first of all, we have to write the system equation. Okay. So we know that the input is f of t and output is y. Okay. So this is called displacement here. So if you apply the Newton's law, and as per the Newton's law, your applied force F of t will be equal to m into a. Okay, m into a is nothing but m into d square x by dt square. So it can be represented as d square y by dt square. So d square y can be represented as y double dash plus b into dx by dt. Okay, for this b, which is nothing but dx by dt. So this is a b into y dash and plus k into x. Okay, so ky, which is equal to f of t. So this is the second order equation. So we'll have two differential equations, two state variables for this second order system. Okay, so let us assume that the state variable x1 is equal to y. So this is a differential equation of the second order form. So we'll consider that the differential equation, and for this differential equation, one state variable is x1. X1 is equal to y. X1 is equal to y, and another equation x2 is equal to y dash. X2 is equal to y dash. Then after getting the two state variables, the next step is to find out x1 dash and also x2 dash. Okay, so whenever you're writing the state variable, state space equations, so first of all you have to consider the state variables, so x1 and x2. So here we are assuming that x1 is equal to y and x2 is equal to y dash. And then immediately writing the x1 and x2, you need to write up the differentiation. So x1, okay, so x1 will be now x1 dash, okay. So here x1 will be x1 dash, and then x2 will be x2 dash. So what is x1 dash? X1 dash is equal to y1 dash, y dash. So x1 dash, if you take a differentiation here, so it will be differentiated. So y dash. So y dash is equal to x2 because y dash is assumed as a x2. And then x2 dash, now you take up x2 dash. X2 dash is equal to y double dash. But from our equation number 1 here, from the equation number 1, okay, so y dash, y double dash is equal to, y double dash is equal to 1 by m. Okay, so here this m will be taken to this side, f of t, because your input is there, f of t minus of b y dash plus minus ky divided by m. So this can be taken as 1 by m into minus of b y dash plus k into y plus 1 by m into f of t. 1 by m into f of t. So this is your input, okay, and here these are the outputs, so state variables. So y dash is assumed as a, y dash is taken as x2, okay, and y is taken as x1, and therefore your equation is of the form, okay, so your equation is in the form of x1 and x2 and also the inputs. But your first equation is x1 dash. So x1 dash will be equal to 0 times of x1, 0 times of x1 plus 1 into x2 plus 0 into u input. Okay, and then x2 dash. This is the x2 dash. Okay, x1 dash. So x2 dash is equal to minus k by m into x1 minus b by m into x2, okay, then plus 1 by m into f of t, okay. F of t is nothing but your u, the input signal u, okay. So f of t is considered as a u, and therefore in a matrix form, if you write in a matrix form, this can be represented as x1 dash and this is x2 dash. So this will be equal to, okay, so 2 by 2 matrix, n by n, okay, n is 2, so it will be of 2 by 2 matrix. So this will be 0, 1, okay. So these are the state variables x1, x2, x1 and x2 plus b, the matrix b into u, okay. So the first equation is 0, 1, and this term will be 0. And the next one is x2 dash is equal to minus k by m. So this is minus k by m, and this is a minus b by m, and this is going to be 1 by m. Okay, so this is a representation of your state equations. So this is a and this is b, this is x and u. So this analysis what we are representing here, and also your output equation y is equal to cx plus du. Okay, so here we assume that y is equal to x1. So y is equal to x1 means c into x1, only 1. So c is equal to 1. 1 into x1, your output will be 0, and therefore your output equation will be like this. So 1 0 1 0, so this is x1 x2 x1 x2, so this is equal to y. So this is your output equation, okay. And the first one is this one is your state equation. So this is your state equation. So this is a matrix C, and this is your matrix A, and this is a matrix B, okay. So A is equal to 0 1 minus k by m minus b by m, and this is a 0 1 by m. So 1 0. So this is analysis now, okay. So 0 1 minus k by m minus b by m, 0 1 by m. So this is a state space equation, and now this is your output equation. So for this system, you can represent in a block diagram like this. In a block diagram model, it can be represented here. Okay, so when you take up the summing points here, this is going to be x2 dash. So you have to represent the number of state variables. Okay, always you have to take in the form of number of state variables. So here we are having a two state variables, so you have to take it as a x2 dash, and this is x2. Then if you integrate this, you'll get a x1. So x1 is equal to y. So your x2 dash will be equal to x2 dash is equal to minus k by m into x1. So you're taking a signal here, which is nothing but k by m. So this is a plus value. And then next one is from the x2, which is minus b by m x2. So this 2 will be added up here. And then this is a minus. You can take it as a minus. So x2 dash is equal to minus of these 2 plus your input signal f of t into 1 by m, and your output equation y is equal to x1 as it is. So this is a way of representing a state space analysis of a given mechanical system in the form of state equation and the output equation, and also the representing in a block diagram model. Now let's take an electrical circuit. Okay, so if you take an electrical circuit, so the electrical equation is given as R into I of t. Okay, your input voltage ei of t will be equal to R into I of t plus L into di of t by dt plus 1 by c into integration of 0 to t I of t into dt. This will be equal to your input voltage ei of t. Okay, and then what are the state equations here? One is the x1 of t. Okay, so this current through the inductor I of t is one state equation. Okay, and x2 of t is taken as the voltage across the capacitor. V is equal to integration of I into dt, EC of t. Okay, so you can take it as integration of I of t into dt. So this is the second state equation. Now by using this analysis, you can write up this state model. Okay, so here also in this model also you can write it. This is considering the voltage directly EC of t. Okay, and here we are considering the integration of I of t, but your output y of t is equal to I of t only. The output is nothing but I of t. The current through the circuit, we are considering it as a output, and voltage, applied voltage is your input. So this is your input. Okay, and here y of t is the output. So in this case also, but the choosing of your values are different here. Okay, so you can go through these equations. Only the state variable, state model varies. Okay, only here this values will be varies. The matrix B is same, the matrix C is same, but only the state matrix differs if you take up these two different methods. Now this is an assignment for you. So here this circuit is having two masses. Okay, and the equation is also of second order. Okay, then these two equations can be written here, and these are the state variables you are assuming. Okay, and you write up these equations by using these two equations. By using these two equations, you write the state model. Now, next, let us take the system which is given by the transfer function here. Okay, so this is a transfer function which is given to you. For this transfer function, we need to write up the state space model. Okay, so here this transfer function is having the output is C of S, okay, and input is R of S. So I'm writing here the transfer function is C of S divided by R of S, okay, So C of S by R of S is equal to 24 divided by S cube, 24 divided by S cube plus 9S square, okay, plus 26S plus 24. This is the transfer function given to you. So you need to write this transfer function into state space model. So state space model is nothing but this is the state equations, okay, and this is your output equation. So for this, what I'm doing here is just you cross multiply this. Okay, so cross multiplying this, it will give you S cube into C of S. So S cube means this is a differentiation. Okay, three times. So your equation will become C triple dash 9 times of S square into C of S, 9 times of C double dash plus 26 into C dash plus 24 into C. This will be equal to 24 times of R. So C is the output and R is your input. And here, so the order of a system is 3. The order of a system is 3. So you are having a three state variables x1, x2, and x3. So the first equation what we are choosing, this is output. So x1 will be chosen as C, and x2 will be chosen as C dash, x3 will be chosen as C double dash. So once you choose the state variables, then next step is you need to take up the differentiation of these state variables. So the differentiation of x1 is x1 dash, which is equal to C dash. So C dash will be equal to x2, and therefore x1 dash is equal to x2, and x2 dash is equal to x3, and x3 dash is equal to C triple dash. Okay, so normal x3 dash is equal to C triple dash. That means C triple dash is equal to minus of 24, minus 24 into x1. Normally this C triple dash will be equal to minus 24 C1 minus 26 C dash 26 C1 call only C the C, this is 24 into C and minus 26 into C dash and minus 9 into C double dash plus 24 into R. And therefore here C can be represented as x1. So this is x1, x2 and x3. This is R. And therefore this x3 dash will be equal to minus 24 into x1. Okay, and therefore your again the output is nothing but your C is equal to y, the output y is equal to C is equal to x1, and therefore so your model will be represented as x1 dash. Okay, the state model, the state equation, we call it as a state equation, x1 dash, x2 dash, and this is x1 dash, x2 dash, and x3 dash will be equal to, this is a state matrix A, and now this will be multiplied with the x1, x2, x3. These are the state variables plus the input matrix B into R. So x1 dash is equal to x2 only, and therefore x1 term will be 0, x2 term is 1, and x3 term is 0, where input signal is 0. Then x2 dash, and again this is 0, 0, 1. Because x2 dash is equal to x3. Again, the input is not there, so it will be 0. And then x3 dash is equal to minus 24. And this will be minus 26. And this is minus 9. And the last one, the input signal, this will be 24. Okay, so your output equation, this will be equal to 1, 0, 0, 1, 0, 0 into x1, okay, x2, x3 plus your input will be 0 here, d will be 0, input will be 0. So this is a state equation and output equation for the given transfer function of a system. So for this, again here, this is your transfer function. So you can represent this in a block diagram like this. You can represent in a block diagram form like this. So you need to take x3 dash, x3 of t, x2 of t, x1 of t. Okay. So x3 of t will be integration. If you do the integration here, you'll get x3. So again, if you integrate this, you'll get x2. You again integrate this, you'll get x1. Okay. The final value is y1. Then x3 dot t will be equal to minus 24 into x1 minus 26 into x4. So this is a minus value, minus 24 into x1 minus 26 into x2 and minus x3 into minus 9 into x3 plus 24 into r. So this is a way of representing your system in a block diagram model. And you can also represent this in a signal flow graph model by taking all the values here. Okay, so this is your r of t, your signal r of t, the same model. Okay, and r of t, and this is your x of t, x3, we can call it as x3, okay, of t. Then this is x2, this is x3, x3, x2, x1, y1. So this is 1, this is y, this is x1, and this is x2, this is x3. So if you want to get x3 to x1, this should be 1 by s, and this should be 1 by s. Okay, and this should be 1 by s. And here this is having a magnitude of 24. Then x3 will be having, with the x3, this is a minus 9, and with x2, this is minus 26. Okay, and with x1, minus 24. Okay, so this is a signal flow graph representation for any given system. Now, so are you listening here? Do you have any doubts now? Do you have any doubts here? So shall I continue or stop here? Shall I continue or stop? Okay. So it takes 2 more hours to finish this. Okay. So once again, you go through this. So we'll see the state space representation for the systems in a canonical forms. Okay. So after seeing this, we'll see the state space model to transfer function model. Then we'll see in the next class, we'll discuss about these 2 points. Okay. So canonical forms and also with the transfer function to state space model and state space model to transfer function model. We'll solve some problems in this. Then we'll see the controllability and observability. Okay, so I'm stopping here. So tomorrow, shall I take class from 9 to 10? Do you have a STLD class tomorrow? Tomorrow, do you have STLD class? Okay. So actually, I'm planning to finish tomorrow. So tomorrow I'll take a class from 9 to 10 and also in the afternoon 2 to 3. Are you ready to attend? Yeah. So I will take a class from 9 to 10 tomorrow. Okay. So after that, we'll decide to take in the afternoon or not. Okay. Okay. Right. Bye.